today. So this is a talk that's, in the talk I'm going to be more high level than I am in the paper. There's a lot of details here in the paper. I'm talking about a type inference algorithm. I do have it on a slide, but it's after the last slide, in case you really want to see it. Putting a type inference algorithm up isn't going to get us too far. But I want to explain the context in which this exists and exactly what we've done. So we'll start off with a little diagram of the context. And this is not the whole context, I can't fit it all on, I've just picked out some bits of the history of this that people might find familiar. In particular, I want you to understand the Stratego, which is a term rewriting language. And from Stratego came something quite familiar to most people here, I'm sure, the Scrappy boilerplate papers. We at Macquarie have Pyama, which is a Scala implementation, amongst other things, of Stratego. And so Scrappy boilerplate, clearly data type generics in Haskell. And as a part of trying to understand how Scrappy boilerplate related to all the other data type generics in Haskell, and indeed all the other data type generics, Hinza has a couple of papers, Scrappy boilerplate Reloaded and Revolution, which pulled out the underlying data structure that Scrappy boilerplate uses, because the data structure has a very strong influence on the flavor of the data type generic system, sums of products versus recursive inductive definitions versus, in this case, the spine view. So Hinza calls it the spine view, and that's what we call it here. But also in Sydney we have Barry J doing some work on the pattern calculus, or quite a lot of work on the pattern calculus, which is related to the row calculus. There's a certain equivalence that Barry's been able to draw between them. And the row calculus is a theory of term rewriting. So we've got this loop almost happening here. And off the pattern calculus there exists an implementation called Bondi, which you can type in code and get an answer. There's lots and lots of bits and pieces in Bondi. So we recognize that the pattern calculus was using the same view of data as Scrappy boilerplate that was expressed by Hinza there in Reloaded and Revolutions. And so we want to fill in the gaps in between here very explicitly between the theory side of things and the practice side of things. So very specifically here, we want to answer the question, or we want to do this thing, precisely characterize the type inference machinery needed to support the spine view of data. And the spine view of data in data type generics can't exist by itself. We need to have a few other bits and pieces, some runtime machinery and type index functions in particular. But we'll keep that aside here. They're orthogonal. The type index functions in the view of data are largely orthogonal. This week we're just looking at the view of data. This work exists in a larger context of a compiler we wrote that does all of the bits and pieces of generics as a kind of exploration of how you can do data type generics, if you're doing a full compiler from the ground up. And in there's type index functions, but not in this particular way. And the results are very small and nice. Okay? It took a long while to get there. The results of this work is that a small extension of Hinza-Milner, in fact, a small extension of Hinza-Milner, now it's getting silly, but is enough to do type inference on the spine view of data. And the reason we pull it back to Hinza-Milner is because what we're interested in here is precisely characterizing. If you were to walk along, you come along tomorrow, you want to make a new language, or build up a theory of something, and you need the spine view of data, or you need some data type generics in there, what's the minimum thing you need to start from? And the minimum thing is important because we want to be able to prove things about these systems. We're kind of in the land of saying, what can I prove about the system? Not just can I implement and what can I see what it does. We've got a compiler that does that. That was fun and interesting. And then we moved on and said, what properties can we prove of the underlying system of the compiler? So obviously you can prove lots of properties of the things up here, but for example, type inference is one of them. And you can demonstrate lots of properties of things down here, and type inference certainly exists. So let's try and find the middle ground. So the two things we discovered is that just a single new expression in a language that's basically Hinza-Milner is enough to do the spine view of data. And then you only need a small extension to the inference algorithm to support a single extension quantified type variable, just in one context, and you can do everything else. I mean, in retrospect, we look back at it and we think, yes, okay, that's maybe not obvious, but that fits nicely. Now, this work is not just Scrappy boilerplate done in theory, but in an audience like this one, I assume that most people are going to be comparing the spine view and the things I'll show you later to scrap your boilerplate. So I want to be very explicit about what we do. And this is, I think, a good way to understand it. So scrap your boilerplate is an example. It uses the spine view, hence it shows that, and it does type inference because you put it into your compiler and GHC works out the types for you. So done. What am I even here for? But scrap your boilerplate does all this in the context of a very complicated, well, very powerful type system. In particular, type classes and type inference directed by annotations on arbitrary expressions, kind of algorithm M back and forth inference, is available in GHC and absolutely necessary for making scrap your boilerplate work. Now, if you're coming from a different language or a different background, or you want to start from a very small system, you can't rely on the presence of things like that. So we wanted to ask the question, is the type inference for spine view possible without those things? And of course, the answer was going to be yes, because we could come up with something isomorphic to those things, but we wanted to try and come up with something as simple as possible. I put in hidden GHC generally with a question mark here because invariably when I'm trying to work out how something gets done in GHC, it's something I haven't quite understood. But as far as I know, it's just the type classes and the multi-directional type inference with the annotations on terms that's required to get the spine view to work in scrap your boilerplate. And the way to convince yourself of that, if you're not already, is just to notice that the scrap your boilerplate needs everything to be an instance of data, which is a type class, so that it can expose certain functions under the values. Now, some of you will go, spine view, yes, I already know what that is, but most of you probably won't, so I'm going to be clear about what the spine view is. This here is the normal view of data, which I call the fully applied constructor view. And it's called, I call it that because data is a constructor plus all of its arguments. And in this case, we're doing a small tree with nodes, with values in the nodes. So this value in Haskell or any other functional language is represented by this piece of data. A constructor has a number of arguments. This one has 3 arguments. This one has 0 arguments. We're assuming that the integers are an infinite set of 0 argument constructors, so this one has 0 arguments. But a node doesn't exist as a piece of data until it's got all 3 of its arguments. If I cut this off here, what does it mean? Well, the thing that's left is no longer a piece of data, it's now a function. A function that's expecting one of these before it can become a piece of data. And the reason that matters is you can't pattern match against this thing. That's what's different about data versus functions. You can pattern match against data in a case expression. You can't pattern match against the function. You certainly can't pattern match against a piece of data that's waiting for a bit more stuff before it can get its answer. So the normal pattern matching that we do with the fully applied constructor view is we enumerate all the constructors with the arguments and some expressions to run. I put down here just a kind of mathematical notation version of that, where we have a pattern matching lambda expression that says run this one if you've got this constructor, run this one if you've got this constructor, and some way to choose between them variously. There's lots of different ways. Well, there's a number of different ways to do the semantics for that. Now, the spine view, this is the same piece of data shown as the spine view. And what we've done is we've reified the application that's implicit in here. So this notation in Haskell, for example, is exactly the same as if node was a function and we gave it 3 arguments. In which case, that would be the application of leaf to the node function, and then the application 3 to that function, and the application leaf to that function. So we treat data exactly like that. We just imagine that application maybe as some other type of application called data application, or maybe as exactly function application. And then we can review the data like this. And it's called the spine view because you get this spine of, I'm going to call them data application nodes today to distinguish them from normal application, off which the arguments hang. So you can see that node has 3 arguments because there's 3 things hanging off its spine. You can see that leaf has no arguments because there's nothing hanging off its spine. So the same data is still there, it's just in a different form. The exciting thing about this is that there's only 2 types of nodes in this system. There's nodes of arity 2 and nodes of arity 0. Nodes of arity 2 are the data application nodes. And nodes of array 0 are the constructors, regardless of whether they're constructors that take arguments or not. And if array 0 that takes arguments, then it's something that is on spine. That means that we can pattern match according to the spine view with 2 cases for everything. We don't need to enumerate all the constructors, which would restrict us just to one data type. These 2 cases match anything. That's very nice. So what's saying here at this point, this is the kind of car and CUDA approach of Lisp. And so one other, if I was in a different audience, I'd be explaining this as Lisp with type inference for bits. So we've got the data application over 2 arguments x and y, and then run some, execute some body. You have to excuse me if I use imperative terms. I'm teaching object-oriented class at the moment. All of this is happening without side effects. And then the other one, which is the constructor, we don't name it in this one, and then you execute the body here too. So here's a kind of a mathematical notation we might have for this. It's not just the one we might have, it's the one we do have, and the one that works for type inference. There are other ones you could do. You could, for example, do a pattern matching lambda here, where you say pattern match on this pattern, give that body, pattern match on this one, give that body, and indeed that's exactly what the pattern has. But that doesn't provide what we need to do type inference. So one of the things in this work is we say, no, don't show this view of data through extended pattern matching lambda. Do it through a construct that explicitly takes in the piece of data, that names the piece of data that it's working on. It's a general name, and then breaks it up. And the semantics for this is, if the piece of data you gave me is a pair, or is one of these, triple, then bind x to the left-hand side, y to the right-hand side, and x to be 1, else x to be 2. And that semantics is enough, yes?
Because so you don't get hold of the name or anything about the constructor, the underscore that?
No. So E2, if E2 needs to use the name of the constructor, it's got it as D. D's in scope for E2. So in the same way here, E2 could use C if it really needed to know what this was bound against. So the semantics of this is enough to express things according to the spine view, and all the examples that we see, for example, in the pattern calculus and Bondo and reload and revolution work, can be expressed this way. So what we've done is we've shown how to do type inference for this. And the reason this is interesting, well, exciting, I think, is because this E1 is an arbitrary expression that uses x's and y's. And getting a type for x and y is interesting. So the example I'll give you guys, normally the example I would give is the kind of everywhere or all top-down that applies a function everywhere in a structured piece of data regardless of the structure, because that's an example of data type generics. But you're all on board with data type generics. So instead, I'll show you GMAP-T, which only goes 1 level deep, and it's the scrap of boilerplate example. GMAP-T is what it's built on, well that's built on default, that's on the next slide. So what this does is it applies a function f to every immediate child of a constructed value. The node 2, 3, if we're in that top node. Not further down. And so we bind x and y against the left-hand side of the spine, the right-hand side of the spine. And importantly, this ends up being the constructor and all the arguments but the last. And this ends up being the last argument. One of the things that Barry J worked out, I mean, lots of people worked out, but I got from Barry J, is that you've got to do it that way. You can't do the binding the other way. And that's the last argument. And we then apply the function to that last argument, and then we recursively call GMAP-T on the rest of the spine, the further. And if we get to the end, we don't actually want to apply it to the constructor stuck on the end, so we just want to D. So what we've come up with basically is an algorithm that can infer the types in an example like this. So let's go through what the types would have to be, and then explain how it works. So the type for GMAP-T has to be, but in type class land, the function has to be a polymorphic function. In fact, without the orthogonal type index functions, it has to be identity. But if we've got the orthogonal type index function, we can put something else in there. Then it'll take in a piece of data, of any type and return something of the same type. We don't know what it is yet. Okay, that means F has to be of type for all alpha to alpha, and D has to be of type beta. And then that means if D was a pair, if D was like a spine, then the type of X has to be something, a beta waiting for one argument. So the same type as a function, it will take a something and give you back a beta. And then the type of Y is that something, whatever the something is. And it turns out that if you view it this way, if you've got the is paired expression here, and a variable here to which a type variable can be attached in the type inference algorithm, all you need to do to make this work, and when I say work, I mean the soundness and completeness proofs will come out, is existentially quantify the variable, the type variable gamma, so that it can only bind against itself. And that's very restrictive, and in most cases, the only thing that will allow gamma to bind against itself is that if the function you apply to y is alpha to alpha. But because there's type index functions, there's a lot of different alpha to alphas. And it could actually be, there are examples I can construct where I'm spitting out something more specific, right? It looks like it's taking an alpha to alpha. It always gives me back a tree, and the type inference algorithm works that out. So only in the body of the in do you have to existentially quantify the type variable gamma. And because we haven't relied on a binder to do it, the type inference machinery's got everything it needs at this particular point to make the decisions that's required.
Question, where does the type of Gmap T come from? I mean, you only see it's a two-array function.
Where does it come from?
Yeah, I mean,
Well,
the code just shows it's a two-array function. It is two lambdas in a body.
That's right. So the type inference algorithm infers a type variable for that, and infers a polymorphic type for that.
Yeah, but it could quantify over many bound type variables.
Oh yes, it could. These don't have to be out for beta. This is just the example. Just try and show that the machinery that's required and why the D. I'll get a bit further through. Maybe that'll answer the question, because there are plenty of holes in what I've shown you here. This is a simplified version, so that it makes some sense. And then just as a demonstration that this can do everything that structural workload does, here's G-fold L, but I won't go through that because it's pretty much the same thing. Importantly though, in structural workload example, the type classes that require this, at least in the first instance of it, you have to define G-fold L for every type, but with the spline view, if you've explicitly got the spline view, you can define it once, and it's just there for everything. So there's some wrinkles in here, and what I've shown you here, none of them aren't solved in what we've got, but having shown you that far now with the wrinkles, you've got to be able to put data back together once you've pulled it apart. But what we've shown is that if you use exactly the same semantics as function application, it all works out, which is nice. There are a bunch of higher rank types in there, and in fact a polymorphic recursive type as well, and some of you will realize you can't do type inference for those. So I hit a wall immediately. And the identity functions did nothing in that example. So function application works perfectly for putting pairs back together. There is an existing type inference algorithm that can do higher rank types and polymorphic recursion without requiring type annotation, without requiring a two-directional type inference algorithm, and that's FCP. So by basing this work on FCP, we've gone, which is a very small extension of Hindley-Milner, that was the thing in the brackets on the early slide. We can then extend that another very small amount and get a system that does spline types, spline data. And of course we're assuming that there are type index functions, overloaded functions, that allow the for all alpha to alpha to be something other than the identity.
So do I understand correctly that you are leaving the actual introspection, like getting structure's name, to this type index function?
At this point, yes. Yeah. So, yeah. As I say, at the end you can have a look at the degen and stuff, which does all of that. Usefully for us, FCP, which is first class polymorphism, has the required machinery to do existential type, existentially quantified type variables. Because it allows you to put existentially quantified type variables in the higher rank types. So it all kind of ties together nicely by the time you get to that point. Function application is extended to treat partially applied constructors as functions. I mean, they are already in most programming languages anyway. The is-pair expression is all we need to add the minimal functional programming, to add to the minimal functional programming language, which is in italics because no such thing exists. But if you think about whatever you're working with, pair it right back, then the extension you need for the spline view is just the is-pair expression. And a type inference system which supports polymorphic recursion at higher rank types, FCP, needs only a modest extension to support that extra expression, is-pair expression. It all falls out kind of nicely. Now, it took quite a while to get there. As I said, here's the slide with the type inference algorithm. It's not my intention. We're going to go through this. The important thing is, with all my little annotations here, everything that's not got an annotation on it is Milner in a sense. Everything with green on it is FCP, and exactly the same as FCP, except for an extra side condition, which probably was an oversight in the original FCP. And then this is what's required for the is-pair. So it's actually a fairly simple rule in the grand scheme of things, but it takes a bit of space just because there's so many expressions in there, because we didn't split it out into a binder. So the story we want to tell is that if you're working on a system that starts from human-ish kind of places, you can explicitly add the spline view without breaking type inference in any way, shape, or form with this simple rule. And we've worked out all the side conditions and bits and pieces that make sure it works. Now, there are many, many more details in there. All the details of how that type inference algorithm fell out and the proofs that it works and all that kind of thing is in the actual paper. And this work has come out of the thesis work I did years ago, where I was taking a bigger picture on compiling generics. And so there's a whole compiler that actually has underneath it an earlier variant of the type inference algorithm and type index functions and all kinds of things that we can play with if you want. And Kayama also is a term rewriting system. We've got Macquarie that Tony Sloan looks after that actually under the hood uses the spline view as well. It's a very generic, and that's an object-oriented language system. Okay, so that's it. Thanks. I've got extra slides. That's for other details that we don't want to go over. Okay.
Thank you, Matthew, for that very clear presentation. And we can see that we use a small extension and we can convert include HYB in that system. So that's very nice. Just kind of trying to connect to the keynotes today. So Frodo talked about that we have traditionally used library approaches to general programming, and we have learned a lot from those experiments. And it seems to be that now it might be a time for us to put what we have learned to language designs. And it seems that your talk will right into the argument. Do you have anything to say on that?
Yeah, that's exactly the motivation I had when I started the PhD. It's far too big a thing to take on, but I wanted to make a compiled language with generics built into it. I wanted to see what the consequences of that were. And I got to the end and I had the language. And so now this is one of the things. There's a couple of others, but they might be things that actually already exist elsewhere that are just described in a different way. With just a few little things that you can build at least this view of data type generics. It's important to note that this view is value oriented, it's very simple, but it loses something. If you've got your normal list of things that data type generics can do, it can't do read, for example, because there's no type information in the view of data. But it explains a version, the type spline, the lifted spline that extend upon that. So now this work we intend to extend so that we can do the full catalogue of generics. But that's exactly what DGen is and what the thesis there is. It's a detailed explanation of what bits and pieces need to be added to a small functional language to make generics work at runtime, and demonstration that it was almost as fast as World Chakravarti's fast and easy generics.
The next question is, you didn't emphasize so much on the talk, but in the paper, you think that the work is solely motivated by the desire of having complete inference.
Yeah.
But we also can see that the is-pair construct is a very convenient term all those combinations.
I agree.
So why is the complete type inference so important, and less so about the term level?
So one of the reasons is because you can find analogues for his pair in lots of different places. In particular, in Sydney, they're playing in pattern calculus, and if you're talking to functional programmers more generally, then they come through this. And there's so many different libraries expressed as well. The semantics of doing the spine view with one expression is interesting to us, and it took us a while to get there. We went through a number of alternatives. But the thing that we thought people would be most convincing about what was new here is that it allows you to do type inference rather than and that really demonstrates that it's a particular and important and useful way to encode that view rather than a lot of the others which are available. But I think that's a harder argument to make just straight up, is to say, look, we've got this particular encoding of spline view and we like it better than the other.
I have a few more questions, but I think we're running a bit late, so I open it to the floor first. Any question? Okay, I'll just go on. So you have summarized very nicely that the problem of type inference boils down to a kind of box is essential type, right? Which is something we cannot know how to deal with. But at the same time, you make heavy use of this ICP.
Yeah.
It seems that a lot of problems, polymorphic recursions and higher rank types are solved by FCP instead of what is here. So my question is, have you tried to use ICP for other spine view encodings directly, and how much kind of annotation could be removed?
Oh, I see. So there's a trick here, a caveat with FCP that I haven't explained here, which is that if you encode with FCP, you're basically trading on type annotations for data annotations for constructor. So in case, see if I can. So when you're actually using FCP directly, you end up with quite difficult to read terms. So here's an example of one. This is a similar function to the GMAP-T, but recursive, done with the no type annotations, but with constructor annotations instead to make FCP work, and it's really difficult to read. So one thing I have been interested in is, well, how does FCP, which doesn't require a two-directional type inference algorithm, relate to all the other versions of type annotations like HNF was my favorite one, but the ones that are GHCs and James talked about, and various others. How do they relate to FCP, which is a one-directional algorithm, but with all these extra annotations? And the short answer is that FCP requires a type-directed transformation, which is not a great thing in a actual implementation. If you put annotations on the terms instead, which is the alternative, you get something that's much nicer for the programmer, but where you've lost that property that we felt was important, which is pairing right back to a one-directional algorithm. And so that's why FCP doesn't have a lot. Like that's why it's not. I've not spent a lot of time trying, because I know exactly how to make the annotations go away, and it's by making the terms much more complicated. Yeah.
Okay. Any more questions before we go for lunch? Right. Let's start. Thank you.